by your mutual gravitational attraction, so we and the Andromeda Galaxy to million light-years away. We are falling towards one another even in the middle of the expansion of the universe. The Milky Way and Andromeda, the massive galaxies in our cosmic neighborhood, are on a slow but inevitable collision course. While this has long been known, and each galaxy is, let's say, around the size of the Milky Way, some are bigger, some are smaller, but the Milky Way has 400 billion stars in it. It takes light over 100,000 years to cross a galaxy. New research suggests the timeline for this colossal event may be shorter than scientists once thought. What does this mean for the future of our galaxy and our solar system? A closer look at the Milky Way. The Milky Way might look like a smooth hazy band in the night sky, but in reality it is a huge and active system. Its shape is that of a barred spiral, which means there is a central bar-like structure made of stars with curved arms reaching out. These arms are filled with star-forming regions, glowing nebulae, and massive clouds of gas and dust. Inside this galactic disk, stars orbit around the center at speeds of hundreds of kilometers per second. Despite those high speeds, it still takes our Sun roughly 200 million years to complete one full orbit around the galactic center. The galactic center of the Milky Way is about 26,000 light-years from us. At the very heart of our galaxy sits a supermassive black hole called Sagittarius A. It has a mass about 4 million times greater than that of the Sun. Although black holes have a reputation for being very destructive, most of them, especially the ones at the centers of galaxies, do not actively consume all nearby matter. They mainly influence the orbits of stars around them through their powerful gravity. If a star or gas cloud comes too close, it can be pulled in. Otherwise, the black hole can stay quiet for long periods. The Milky Way is surrounded by a galactic halo of older stars and globular clusters. Globular clusters are tight-knit groups of stars that are often very old. Some are almost as ancient as the universe itself. These clusters orbit the galaxy outside the main disk, and they help astronomers understand how the Milky Way grew over billions of years. Studies reveal that our galaxy has absorbed many smaller galaxies in the distant past, leaving behind traces like streams of stars in the outskirts of the halo. Beyond the halo are satellite galaxies that orbit the Milky Way. The most famous are the Large and Small Magellanic Clouds. Visible in the southern hemisphere, they are irregular dwarf galaxies that may eventually be pulled in and merged with the Milky Way over huge time scales. Our home star, the Sun, is roughly 2/3 of the way out from the center of the Milky Way in a region called the Orion Arm or Orion Spur. This location is relatively quiet and not too close to dense star-forming areas or the central black hole. It is also where Earth resides. Our galaxy contains at least a couple 100 billion stars, but some estimates suggest there might be even more. Astronomers are still trying to refine these numbers as new telescopes and projects provide better data. The Andromeda Galaxy and its importance. The Andromeda Galaxy, also known as M31, is one of the brightest galaxies we can see from Earth without a telescope. It lies around 2.5 million light-years away, which is extremely far in everyday terms, but quite close by cosmic standards. Andromeda is a spiral galaxy, much like the Milky Way, though it is often said to be larger in overall diameter. Some measurements show that Andromeda might have more mass, while others suggest that the two galaxies could be closer in mass than once thought. Regardless, it is the biggest member of the local group, which also includes our Milky Way and about 50 smaller galaxies. Like our galaxy, Andromeda has a bright central bulge and several spiral arms that hold giant clouds of gas, dust, and many stellar nurseries where new stars form. At its center, Andromeda is believed to have a supermassive black hole with a mass possibly comparable to or larger than that of Sagittarius in the Milky Way. Andromeda also has a network of globular clusters orbiting it and dwarf companion galaxies in its immediate neighborhood. In the early 20th century, astronomers debated whether Andromeda was just a nebula within the Milky Way or a separate island universe. The resolution came from measuring Cepheid variable stars, special stars whose changing brightness can help determine distances in the Andromeda Nebula. When they realized it was millions of light-years away, it proved that Andromeda was an entire galaxy of its own. Andromeda is important to astronomers for several reasons. It is close enough that we can study its structure in detail. Observing star-forming regions in Andromeda helps us better understand how specific types of stars are born. Researchers also keep track of the motion of Andromeda relative to the Milky Way. which is crucial for predicting what may happen when both galaxies come together in the far future. For a while, scientists estimated that Andromeda was moving toward us at about 120 kilometers per second. Thanks to better instruments, these measurements have been refined. But it remains clear that Andromeda is on a collision or near-collision course with the Milky Way. In broader terms, the local group itself is moving through space, pulled by gravitational forces from other large structures in the universe. But that does not lessen the big event scheduled to take place billions of years from now. Why galaxies collide? A galaxy collision happens when two or more galaxies move close enough that their mutual gravity begins to pull them into each other. While collision might make you picture stars smashing together in chaotic blasts, most stars inside galaxies have lots of empty space between them. Because of that, individual stars can pass by each other without smashing head-on. However, the galaxies as whole entities become distorted and twisted during a merger, and that process is both visually stunning and scientifically significant. Collisions can range from slow, peaceful merges to intense, high-speed crashes. When the approach speeds are lower, perhaps a few hundred kilometers per second, galaxies are more likely to merge and become a bigger galaxy. These collisions can cause bursts of star formation as gas clouds crash together and collapse into newborn stars. Tidal forces from the combined gravitational pull fling streams of stars and gas into wide arcs, sometimes creating tail-like features. Over millions of years, the two galaxies gradually settle into one cohesive unit, often turning into an elliptical galaxy, if both galaxies were about the same mass. In more extreme situations, when galaxies approach each other at speeds around 1,000 kilometers per second or more, the collision can be more violent. The gravitational forces can tear the galaxies apart in a shorter time frame. Some stars may be thrown out into intergalactic space, while others become part of strange or twisted shapes. These events might not always end in a neat merger. Instead, the galaxies could be left as scattered pieces that slowly move away from each other, their shapes forever changed. Researchers study galaxy collisions by observing examples throughout the night sky. Telescopes on Earth and in space have captured many interacting galaxies as stages from first contact to final merger. For example, the antennae galaxies in the constellation Corvus are well known for their long, star-filled tidal tail. Another famous pair is the Mice galaxies, named for their long tails created by tidal forces. By watching these interactions, astronomers can reconstruct what might happen to the Milky Way and Andromeda, as well as learn more about the growth and evolution of galaxies across cosmic time. Dark matter's role in galactic interactions. When two galaxies collide, the visible stars, gas, and dust are not the only factors at play. Most of a galaxy's mass is thought to be dark matter, which does not give off light or other forms of electromagnetic radiation. Scientists first realized that galaxies contained large amounts of unseen mass by measuring the speeds of stars orbiting the galactic center. The stars near the edge of galaxies were moving too fast to be explained by just the mass we can see. This implied that something else, dark matter, was providing the gravitational pull to keep those stars in orbit. Dark matter's exact nature is still a big mystery. Astronomers and physicists believe it consists of some type of particle that does not interact much with normal matter. However, it exerts gravity just like anything with mass. During a galactic collision, the dark matter halos of each galaxy may pass through each other almost unchanged, because dark matter does not collide and scatter the same way normal matter does. This halo collision can still affect the motion of stars and gas, shaping how the galaxies end up merging. Simulations of colliding galaxies use both the visible material and the dark matter component. These computer simulations have become much more realistic thanks to expanding computing power and better data from large telescopes. Scientists can input factors like mass, velocity, and the distribution of stars and dark matter. By running these simulations over billions of years in fast motion, they can see the final shape of the remnant galaxy and compare it to real observations. This helps refine our theories about how galaxies build up over time. Aside from fueling collisions, dark matter also clumps together in structures described as cosmic webs or filaments on very large scale. Galaxies often form at the intersections of these filaments. That is why clusters of galaxies appear to be linked in a giant cosmic web across hundreds of millions of light years. Within that web, collisions and mergers are an essential piece of the puzzle. They drive galaxy growth and evolution, recycle gas into new stars, and sometimes trigger powerful outbursts from supermassive black holes at galactic centers. Dark matter's gravity is the silent hand guiding much of this action, reminding us that what we see in space is only a fraction of what really exists. Measuring distances, velocities, and collision timelines. To figure out when and how galaxies will collide, scientists need accurate distance and velocity measurements. One main tool for measuring distance in astronomy is the use of standard candles like Cepheid variable stars or Type Ia supernovae. Cepheid have a well-known relationship between their brightness changes and their actual brightness. So by measuring how bright they appear from Earth, astronomers can estimate how far away they are. Type I supernovae have a consistent peak brightness, making them useful for measuring even greater distances.